Okay, so when we say virtualization, very often we mean what is called system virtualization. So you take a computer and you essentially virtualize the entire computer system. And there are two uh, you know uh, concepts related to virtualization. One of them is virtual machine monitor, also called a hypervisor. So the VMM is the software layer that's responsible for providing this virtualization. So everything in the underlying machine, the underlying system is uh, being made available. You can access them by using this hypervisor. So you can think of the hypervisor as some sort of a mini operating system that essentially whose responsibility is to virtualize all of the physical resources, and then the real operating system, the full operating system, will then sit on top of the VMM, right? So this uh, operating system and the processes on it together, we refer to that as the virtual machine, right? So the virtual machine is running on top of the virtual machine monitor. So virtual machines are not new. So they have been around since the 1960s, because in the 1960s, the concept of multi-user operating systems hadn't been developed. So the operating systems were strictly single user, but obviously you could not dedicate the resources of a computer to a single user, because obviously in the 60s these things cost millions of dollars. So the idea was that each user can, the way to share this costly resource across different users is essentially by virtualizing the whole thing, and then allowing one user to use a virtual instance of this mainframe for the duration of running their job. Okay, so their uh, application or whatever is used to be called a job, and this job would be run on one of those virtual machine instances. So virtual machines continued to be an active area of interest in the 1970s, but in the 1980s, with the advent of these mini and microcomputers, people thought, well, now you can have one machine for every user. There is no need to sort of virtualize, and because of this, the potential for virtualization was underestimated in the 1980s, right? And at the same time, the second development that is responsible for this underestimation is the advent of multi-user operating systems. So you could have the entire operating system shared across many users, which takes care of the hardware cost issue, even if you are talking about expensive hardware. And at the same time, you also have these small, availability of low-cost hardware on which you don't necessarily need this sharing. So you had this development of more or less single-user operating systems on, mini computers. So like things like MS-DOS, and also you had these multi-user operating systems that would run on workstation or server type machines, and Unix was belonged to that category. Then as time went on in the late 1990s, there was a resurgence of interest in virtualization, and this was sort of more of a bottom-up development, because people figured out that there is an efficient way to do virtualization for the commodity hardware, which is based on Intel x86 processors. And once this technology became available, then virtualization software became available, and then people realized that there are many more things you can do using virtualization that they didn't think about before. So one of the advantages is that you can you know, have data centers where you have, you know, lots of, you know, server type machines sitting in the data center, and then people can host their, you know, virtual machines in the data center. This way, you know, people have access to, you know, these entire operating systems if they want. At the same time, they don't have to bother with managing the hardware, right? And it also made it possible for doing many other things, like, you know, people could, you know, you could have an operating system running on one machine, and then, you know, if that hardware needed to be, you know, rebooted or powered down, then they could essentially, you know, freeze the state of the operating system and move it over to another piece of hardware. And this way you can increase, you know, availability, because you don't have to, you know, really reboot the operating system simply because you have to, you know, shut down the hardware and things like that. So people realize that there are a number of benefits to using this type of virtualization, and then it took off in the 2000s, and now with the advent of cloud computing, virtualization is everywhere. So any questions so far? Again, unmute yourself, ask a question. Sometimes when you don't ask any questions, then I don't even know whether there's anybody there or not.
Professor?
Yeah.
The concept of Docker, which is of the containerization, which is like I have heard in like last 2 years. So like how is that is related to like these virtual machines?
So I don't know exactly what you mean by a broker. Broker is
No,
a
uh,
term.
I'm talking about Docker. D,
Docker. Oh,
yeah.
Docker is something that we will talk about it at the end of the, towards the end of the lecture. So, you know, on the current side, you'll already see Docker somewhere if you look through the entire slide. Any other question?
Yeah.
Okay, so there are three types of virtualization. The first one is called process virtualization, which means that you are virtualizing just a single process. And this is essentially what all these dynamic binary instrumentation frameworks do. So we have talked about DynamoRio and PEN, and both of them are essentially virtualizing a single process. And so they basically you know, take the code of a single process and then run it inside a virtual machine, which is this dynamic binary instrumentation system. Okay, so another example is the Java virtual machine, right? Because again, you know, you are running a single application which runs as a single process, and that single process is really the Java virtual machine executing the bytecode for your Java application. Okay, so this is all you know, what is called process virtualization, and by and large, that's not what we are going to talk about today. The second type of virtualization is called operating system virtualization or namespace virtualization, right? So the point is that you have a single underlying operating system kernel, right? So there is just a single instance of the operating system that's running. But this single instance creates the illusion of multiple operating systems running on the machine. So this solution is created for the applications that are running on top of this operating system. And the way this happens is that inside the operating system, every virtual instance resides in a separate namespace. Okay, so the namespace can refer to you know, every object. So the most obvious example of an object is a file. So each of these virtual machines will have a different file system. But in addition, they also have different uh, process ID namespace, user ID namespace, and so on. So the processes that are running on one virtual machine see their own set of files, their own set of process IDs, and their own set of devices and whatnot. Whereas a different operating system instance is going to have its own different namespace. And Docker is an example of this type of namespace or OS level virtualization. And its main benefit is that you have only a single operating system running, and therefore there is much more effective sharing of the underlying resources. Whereas what we refer to as system virtualization or full virtualization, that happens when you have separate virtual machines, each running their own instance of the operating system. Okay, so the operating systems running on each virtual machine is completely different. And as a result, of that,
You are no longer sharing the screen.
Right, so it went to sleep because I wasn't touching it often enough. So now I guess I probably have to unshare and share again. Okay, so the difference between OS virtualization and system virtualization is that in system virtualization, if you have n virtual machines, you have n different operating system kernels that are running, and therefore it's each operating system instance needs its own the resources needed for running each operating system instance that cannot be shared, and therefore you end up having a much bigger footprint. So while you might be able to run hundreds of Docker container on a server machine, you would be hard pressed to run a dozen fully virtualized operating systems on the same hardware. So that is the reason why namespace virtualization has become very popular. But from a security perspective, namespace virtualization is not that effective, and we'll talk about that later. And this is the reason why we will talk about system virtualization. Again, when you go to Amazon or any other cloud provider, and you get an instance of a system that you can use for your purposes, you typically are getting a fully virtualized system, which is running, where you basically get a bare machine. You can install your operating system on top of that, and you can do whatever you want on top. So so when you go to the cloud, you often are getting you're dealing with full system virtualization. And this is also sometimes called as infrastructure as a service. Right, so you often see this term IaaS, which means that infrastructure as a service. And that's what you get from, when you go to Amazon cloud or Microsoft cloud. This is typically what you get from there. So let's look at how exactly this works.
Excuse me, Professor?
Yeah.
I still am not entirely sure what the difference is between running just a virtual machine and running one of these Docker containers. I understand that the OS kernel isn't there, but what if the Docker container is just another OS?
No, so it's the one way to think about it is that the virtual machine, the operating system has been modified to create these distinct namespaces, and then each container, Docker container, belongs to one of those namespaces, which means that they can, run independent of each other, but they are still sharing the same operating system.
Does this mean
so
that
all of the operating system, memory, data structures, everything is shared? So in order for this, container-based virtualization, as it is also called, right? So namespace virtualization is also called containerization, or just containers. So in order for that to work, you are relying on the operating system to sort of keep these namespaces apart. And while it is something that basically works, there are too many things that are still common, which allows which is beneficial in the sense that you have better sharing of the underlying hardware, but it is also problematic from a security perspective because you don't have isolation between you don't have full isolation between what's going on in different in containers, because inside the operating system they are sort of doing the same thing, right? So think of it like multiple users, right? So on a same operating system, right? So with some care, the users can protect themselves from each other, but it is not entirely, achieving full isolation is quite difficult, because there is always some way for one user to find out something about the other user. And so, things are not quite as secure as, you running on a one machine and the other person running on, using a different machine. Okay?
Yes, thank you.
So, so now we are going to talk mainly about system virtualization, or whole system virtualization, or also called full virtualization, right? So there are two types of hypervisors. One is called the type 1 or bare metal hypervisor, where you have the host hardware and then the virtual machine monitor runs right on top, and then you install the virtual machine on top of this VMM. And so the operating system that runs within this virtual machine, that is called a guest operating system, right? So you have host hardware, and then on top of this, there is the VMM, which allows you to share the underlying hardware across different virtual machines. And then each virtual machine runs its own operating system, and on that operating system, there are one or more applications running, right? So this is called type 1 hypervisor. And when you go to place like Amazon, then they are typically running type 1 hypervisors, Okay, so what is the other type of hypervisor? So the type 2 hypervisor is one where there is already a host operating system running on the host hardware, right? So you try to virtualize on top of an underlying operating system. So when you, for instance, install a virtual machine on your laptop, this is what you're doing. You are working with a type 2 VMM, and the type 2 VMM is really running as an application on top of the host operating system. Okay, and this application is providing an environment in which you can run the virtual machines, which means that inside this application, you are instantiating a guest operating system, and the guest operating system, creates guest applications and so on. Okay, so as you can see, you have a host operating system here and a guest operating system here, and so that should immediately tell you that this is going to be somewhat less efficient than the type 1 hypervisor, because the type 1 hypervisor, you just have a thin hypervisor is all that is there on top of the hardware, whereas here you have the hypervisor plus the host operating system running on top. Okay. In addition, there is no longer a single hypervisor. Each virtual machine I'm sorry, that wasn't right. So the real point is that you have two operating systems here, and that means things are going to be slower because there are more layers, more context switches, and more resource usage, all of which lead to sluggish performance, which you would have noticed, right? So when you run a VM on your laptop, it doesn't run quite as fast. So how does this all work? So how does virtualization work? And this slide not only relates to how it works, but also gives you some idea of why virtualization was difficult when the x86 hardware came out. So before we get into this, we need to understand a little bit about how what is the basis of security in what are the hardware features you need in order to build security in operating systems. Okay, so that is based on what is called protection level in your processor. Okay, so typically there has to be at least 2 levels. So, but the Intel processors actually provide 4 levels, 4 protection levels. Ring 0 is the highest privilege, and ring 3 is the lowest privilege. In a typical operating system, whether you take Windows or Mac or Linux, the user applications are running in ring 3, and the operating system kernel is running in ring 0. Okay, so there are many instructions called privileged instructions that the operating system uses. So an example of a privileged instruction is one that is used for setting up virtual memory, or setting up memory permissions and things like that. So all of that require instructions that are generally available only in ring 0. So because the operating system needs to use all of that, it resides in ring 0. User applications cannot and should not use those instructions, because if your application can change the virtual memory protections, then it can read or interfere with processes of other users or the data inside the kernel and so on. And therefore, the user applications should not be running in the privileged with any privilege. And so they should be running in ring 3. Now, of course, one of the problems is that things like doing file I/O, they require access to hardware devices, and access to hardware devices is again something that requires executing privileged instructions, and therefore only the operating system can execute these. Needs to perform this I/O. So the user applications need a way to request the operating system to perform these privileged operations. And the way that happens is that the user applications basically invoke some kind of a software interrupt, and then the operating system code is invoked to service that interrupt. And at that point, the operating system can carry out the request. Okay, so it's important to note that user applications cannot simply call some function in the operating system, because if user applications can call an arbitrary function in the operating system, then it is difficult to ensure that then you can no longer isolate the operating system kernel from the user applications, which means that you cannot protect the operating system from the user applications. So what you need to do is you need to provide a controlled way for user applications to request services from the operating system. So this controlled way should only allow the application to store the request somewhere in memory, and then simply tell the operating system, I have something, I have a request, please process it, okay? Because it only can say, I have a request. There isn't a way to sort of control the user application don't have any ability to control exactly what goes on the operating system side. It is up to the operating system to go examine the request and then decide whether it is a valid request, whether it is safe to carry out that request, and so on. Okay, so this is why when we did the system call interception assignment, we talked about in the fact that in Linux, this interrupt 0x80 is used to make a system call, and again, that the application that's running in ring 3 is putting all of the system call related information in various registers, and then it's invoking this interrupt. And when the interrupt is received by the operating system, it picks up that request and then carries out the system call. And before it carries out the system call, it again checks whether the arguments are valid and whether the user has permission to carry out this operation, and so on and so forth, right? So that way, because the user application is not able to directly invoke any code on the kernel side, the kernel is able to perform all these checks, and only when all these checks are passed, the operating system picks up the request and carries it out. So, so given that, so how can you, given this setup, let's go back and see how we could potentially, do this virtualization. So as we said here, the virtual machine monitor is going to run as a normal application, and in particular, the guest operating system is also going to run as an application. Okay, so now if you simply run the guest operating system as an application, now what's going to happen is that it is going to execute because it's an operating system, it's going to contain privileged instructions, right? So these privileged instructions will get executed, but notice that applications are running in ring 3, therefore these privileged instructions won't work correctly, okay? So one of the problems is that in x86, there are some instructions which, if they are executed in ring 0, they have one behavior, and if they're executed in ring 3, they have a different behavior. And this makes it difficult to simply run the entire operating system as a user level application. Because, well, you know, if it executes this privileged instruction to, you know, say perform an IO operation or something like that, it ends up having a different behavior at the user level, and you don't realize that anything has gone wrong. So, researchers identified the key requirement for running an operating system as an application as follows, right? So they defined the notion of a privileged instruction as something that simply will not execute in the user mode, right? Meaning that if you try to execute in the user mode, there will be a trap, okay? The trap would basically say it's an illegal instruction, right? So the instruction is not valid to execute. And the advantage of having that kind of a exception or a trap is that when the trap is serviced in ring 0, at that point, the servicing routine can realize that this trap is occurring because we are trying to execute the operating system code at the application level. And then it can try to basically, the servicing code can then say, hey, okay, so this is this operating system, so I will try to emulate this, which means that the instruction by itself will work directly on the underlying hardware. When you emulate, you're going to emulate it on the virtualized hardware, right? So that's what you're going to do. And this can be efficiently done because each time you try to execute an instruction that is privileged, you're going to go to there's going to be an exception. But unfortunately, you know, in the case of x86, you have this problem that there may be some instructions which are part of this operating system that you are trying to execute at the user level, but they don't cause a trap. And therefore, if you just try to execute this at the user level, then the operating system doesn't work anymore, right? And so, so people had to find some way to you know, work around this problem. And what they did is they said, okay, so what we are going to do is we are going to you know, look at the instructions one by one and recognize the instructions that you know, could be part of the operating system. And then if they are part of the operating system, then we will actually you know, emulate them. And this required you know, basically looking at the code before it executes. So they developed a technique. So VMware is a company that many of you may be aware of, and many of you may be using the virtual machine software from VMware. The way they got, the company was formed was because they found a way to you know, deal with this problem and develop a technique based on binary translation to recognize these privileged instructions and emulate them, right? And once they were able to do it, then they were able to do full virtualization using you know, binary translation. But what has happened since then is that processors, so Intel and AMD, you know, realizing how how popular virtualization is, they have worked out the problems in the x86 instruction set, and now they provide virtualization features in hardware that allows this sort of execution of applications, execution of entire operating systems at the application level, and then you no longer have this problem that some operating system instructions execute without causing a trap. Instead, the virtualization extensions in the newer processors, they correctly trap whenever an OS instruction is executing at the user level. They trap, and then once it is trapped and goes into the ring zero, the ring zero servicing routine can then realize what's going on and emulate this this instruction. So this problem of having to use binary translation is no longer something that needs to be done. But there was also a second approach for virtualization that was developed, which is called para-virtualization. Okay, so the virtualization approach that we have talked about so far is one where we simply take an unmodified guest operating system and simply run it as an application, right? So that is very attractive because you can take, closed source operating systems like Windows, and you can simply run it, as a virtual machine. And so this is quite advantageous, but the problem is, again, you have to have this, two distinct instances of operating systems, and that causes a lot of overhead. And so people developed a second approach, which is called para-virtualization, which involves modifying the operating system so that it can run on top of the virtual machine, right? So now the operating system is aware of virtualization, right? And so instead of directly going to the hardware, it is going to the virtualization layer. So if you look at the picture from the previous place, so you'll see what is going on, right? So in this case, the user application, right? Here, you take an unmodified operating system and you run it as a user level application, then it is going to execute instructions that directly access the hardware. That is going to cause it, so essentially that's what is this arrow shows. And then that is going to cause a trap, which is going to be picked up here, and the ring zero service routine can then emulate and access the underlying hardware in the appropriate way that gives you the effect of a virtualized hardware. Whereas in the case of para-virtualization, the user application is, so in this case, you have a guest operating system that is already aware of virtualization, and so it does not go directly to the hardware, right? So there is no connect. The guest operating system is not accessing the system hardware, but instead it is going to the virtual machine monitor, and the virtual machine monitor is then going to the the underlying hardware. So in order for this to happen, the guest OS needs to be modified, right? Because the stock operating system thinks it's running on some hardware, and so it's just going to go directly to the hardware. Whereas here, what you need is you need to modify it so that it can go to the virtualization layer. And so this is requires a change to the operating system, right? But then you get better performance because instructions no longer require a trap and emulation, right? So So for instance, you don't have to emulate access to a networking stack by writing to some virtual device and whatnot. Instead, you make a call to the VMM, and the VMM call will do the right thing. So instead of having many executing many low-level instructions that trap and then are emulated, you have higher level operations that can be executed. And this is particularly relevant for things like graphical user interface, because graphics interface, in order to do anything on the graphical interface, a large number of operations need to be performed, and this, if it's emulated using hardware level interface, it just requires an enormous number of traps and emulation. And this is why you would generally notice that things like browsers don't run very well on virtual machines. Whereas if you're talking about server type applications, if you're talking about a web server, those things tend to run fairly well. And in many cases, you may not even notice that you're running on a virtual machine. But anything that relates to user interface and graphical output, you will notice that there is a lot of overhead for virtualization, which occurs because of this trapping and emulation. And that's something that can be made less of a problem using para-virtualization. So Zen is one of the well-known para-virtualized systems, and it is still in wide use today. So I already talked about hardware-assisted virtualization, where the hardware ensures that when you directly execute instructions, privileged instructions at the user level, then that gets trapped and sent to the virtual machine monitor, and the virtual machine monitor can then do the right thing. So I'm not going to go too much into the exact technologies. Several years ago, they were partially developed, and so systems relied on a combination of binary translation-based emulation and the hardware features. But by now, hardware features are very well developed, and so these hardware features are the ones that are being widely used. So, so let me just talk about how virtualization relates to security, right? So one of the things we do is we can use virtual machines for security experiments, right? So that's one of the reasons why we would like to know about virtual machine technology. So for instance, honeypot systems, or if you want to analyze malware, then it's not practical to install malware on your machine and experiment with it, because malware can damage your system. So if you run it inside a virtual machine, then hopefully there is sufficient isolation between the malware and your hardware, and so you can do this analysis without compromising your machine's security. You can also use virtualization to run higher security virtual machines. So for instance, you can run many commodity operating systems may not be secure enough because they may be designed and configured for convenience, ease of collaboration and whatnot. And the same features that make it easy to collaborate and share and so on, also make it easy for one bad application to compromise the security of the entire system. And you can protect against this by having one dedicated virtual machine that either runs a special purpose operating system or it runs a commodity operating system, but you use it in a way that in such a way that you don't expose it to the external world that much. Maybe you use it only to access some small set of websites that are within your organization, and you only install a restricted set of software that is authorized by your organization and so on. And that way, this virtual machine can be more secure, while you may run other virtual machines that where you might that you might use for collaborating with people outside your organization, and then maybe those virtual machines are not as secure. But by creating distinct virtual machines, you can isolate these interactions, and that way keep things more secure. So virtualization can also be used to deal with the possibility of compromised operating systems. So for instance, we have talked about rootkits, where you have software malware that embeds itself into the operating system in such a way that it is difficult to figure out that malware is gotten inside the operating system. And so what you can do is you can rely on the fact that the virtual machine monitor is in many ways much simpler and does not provide much of an interface to the external world. And therefore, it is much easier to ensure that the virtual machine monitor is secure and it is not compromised. And so you can build techniques for say scanning for rootkits inside your virtual machine monitor. So that's another way virtualization helps in security. Okay, but security also, virtualization. So far I mentioned how virtualization can be used in security applications, but there is also the other side of it, which is that virtualized systems bring their own set of security challenges. And this goes back to the fact that we like virtualization because it enables sharing, right? Sharing means cost savings, and this is really why we like virtualization. But the moment you share, that means you have mutually untrusting entities sharing the same processor or same hardware. And this means that there isn't as much isolation, right, between untrusting entities. So if, let's say, organization A has one virtual machine and organization B has another virtual machine, and if both virtual machines are running on the same physical hardware, then there is some sharing of underlying memory and whatnot. And because of this sharing, it may be possible to carry out some attacks. And we'll talk about a particular class of attacks called side channel attacks, which are possible when you share the same underlying hardware. And therefore, these side channel attacks become much more of a problem when you have virtualization. Without virtualization, you have your own dedicated hardware, and therefore, no other entities running on the same hardware, and therefore side channel attacks are not feasible. Okay, so in addition, denial of service becomes feasible when you have this kind of sharing. But in practice, we don't worry too much about denial of service because when you often there is denial of service is detected, and often there are mechanisms to punish the culprit offline, for instance, by throwing them out of the system and then saying, hey, you can't use the shared resource anymore. And so very often denial of service, although it's very difficult to prevent, it's not so much of a problem in practice. And the problem in the security problem in practice is really much more of these side channel attacks, where by relying on the fact that you are running, an attacker is running their virtual machine on the same underlying hardware, they are able to snoop into the activities of another virtual machine sharing the same underlying hardware. So now I want to sort of finish off this topic by talking about Docker, right? So Docker, as we said before, relies on namespace virtualization, right? So in particular, there is each container cannot see the entities that are that can be seen by other containers, right? So each container has its own set of files, its own set of processes, process IDs, usernames, network interfaces, and so on. So pretty much everything that a container can access is not visible to other containers. So that provides a good deal of isolation. In addition, there is a mechanism called C group or control group, which allows resource separation, right? So C group is a resource accounting and limiting mechanism. So you can say that this container can only use so much CPU and so much memory, so much disk IO, and so on. This allows you to sort of prevent one bad container from using up all available resources, such as all the memory or all the IO. And so it provides a better basis for running large number of containers on the same underlying hardware, right? So these are the two key security mechanisms that Docker provides. And your security ultimately depends on how you set up the namespaces and the C group mechanism. So in addition to the isolation, there is another point of vulnerability that you need to be aware of, and that is the fact that there are some shared infrastructure services that run on the host operating system, right? So if you are familiar with Docker, you will know that there is something called a Docker daemon that runs in the background. And Docker daemon is a process that's running on the host operating system. And it's possible to set up the Docker daemon in such a way that the containers can share files or directories with the host operating system. But if you do this, then the container, a malicious process running inside the container is able to then change the files on the host operating system. And in the worst case, because the operating system itself is a file in the host file system, and therefore it is possible for a malicious container to even replace the underlying operating system. So one has to be careful and make sure that the Docker daemon is not configured insecurely, because if you do that, then the containers can do anything. So one of the points to remember is that even though the namespaces are separate, the root privilege or the user ID of 0 is still user ID of 0 on the host operating system, right? And this is a problem. So so one of the things you should try to do is that you should try to use Linux capabilities to make sure that processes running inside the containers, even if these processes are running with root privilege, you should make sure that Docker is configured so that it relinquishes almost every capability, so that even though it is running as a root process, the process running inside the container are unable to do any of the things that root can do. Because if you recall, the Linux capabilities is a mechanism for dividing up root privilege into many small privileges. And essentially, if you disable all of these capabilities, or if you relinquish all of these capabilities, then it's no longer possible to do any of the things that root process can do. And so, so that's how you can further limit, what damage can be done by Docker process. But all that, all that, so all of these things can be done to limit the security, the damage that can result from a malicious container. But still, you are not going to, if you're Amazon, you're not going to let people run containers as much, because, the degree of isolation between containers is simply not good enough to, enable completely untrusting entities to run on the same host operating system. But so again, in the real world, Docker is not so much used for its security features. It is used because it allows, it's a good way to manage dependencies. Because whenever you try to install any application, you'll realize that the application has a lot of dependencies on having certain version of certain other software being available. And if the versions don't match, then this new application doesn't run. And the idea behind Docker is that you can, package all of those dependencies into sort of a virtual machine. And now you just run this virtual machine that essentially runs this one application that you want to, really run. And that's means that you no longer have to really worry about, do I have the compatible versions of other software? Because whatever is a compatible version of the software that you need, that will all be packaged into one Docker container. And this is why Docker is popular, because it allows this kind of packaging of of single applications into essentially a virtual machine. But it is not being, its popularity doesn't stem from security. So security is sort of an afterthought in Docker, right? So because Docker is designed primarily to make it easy to encapsulate dependencies and make it easy to package applications so that they can run on any system. And then security, well, if you're going to run it on any system, then people start worrying about security, and then security features have been added as a somewhat of an afterthought. And that's why it's not as secure as, say, system virtualization, where security was sort of the focus right from the get-go. Okay, so that's all I wanted to say about virtualization here. So we can stop here, and I can take any questions. Any questions?
Yes, Professor.
Yeah.
So I was wondering how some programs like malware are able to detect when they're running like in a virtualized environment?
Good question. So there are many ways to do this. One way is you can try to query the devices on the system, what devices are available, and virtual machines generally use certain devices. For instance, if you look at a virtual Linux guest operating system, it will always be using this E1000 network interface card. So by looking at things like that, they can find out whether they are running on a virtual machine or not. There are many other techniques. One technique that is that researchers have talked about, and a technique that's very difficult to evade. So okay, so again, this ends up being a cat and mouse game. So the moment that attackers find a way to figure out that they are running on a virtual machine, the virtual machine developers start saying, hey, let me just return a fake response. And so they try to return a response that matches a realistic system. And then the attackers then say, okay, now let me look at the next level of detail to sort of see, whether this is really a physical machine or not. So one of the differences is that if you run CPU intensive computation, then it'll tend to run as fast on a physical machine versus virtual machine. But if you run IO intensive computation, then it'll tend to run much slower on a virtual machine, because every IO operation is going to be going to cause a trap to the operating system, and this trap needs to be serviced. So there is a huge performance differential between IO intensive applications and CPU intensive applications. And by detecting this difference, it is possible for to detect that you're running on a virtual machine with almost virtual certainty, and it is very hard for the developers of a virtual machine software to defeat this type of an attack. Fortunately, it's no longer important to hide the fact that you're running on a virtual machine, because these days everybody is running everything on a virtual machine. So this problem kind of disappeared in a way, because everybody is running everything on a virtual machine. But still, if you're talking about environments for doing malware analysis, then you still have this problem that those types of malware, they try to detect whether they are in these specific environments that are designed for malware analysis, and you still are you end up with a cat and mouse game, and it's an ongoing struggle. Any other questions? So we will have our quiz on Wednesday as before. Follow the guidelines. Make sure that you get more practice. Again, I want you to do these quizzes for two reasons. One of them is that I want you to get really, quite comfortable with this way of, taking exams, so that when it comes time to do the midterms or the final exam, it's no longer that stressful. And the second reason is that, especially with this, when we don't meet physically, we don't interact as much in class, and it's easy to tune out it's easy to just say, you know, I'll look at this, listen to the lecture offline, and then, you know, you say, okay, then I'll look at it later. And then it's easy to sort of, you know, fall behind. And that's why we are, you know, making sure that there are quizzes every week to just try to make sure that you stay on top of the material. And then, you know, so that's why we have these weekly quizzes. Any other questions? If not, you know, let's, you know, let's end the class here. Okay, so we'll see you on Wednesday.